Hello and good morning, everyone. I'm Ashley Kilbasa, Product Marketing Manager for Lastline Inc. Welcome to the fourth and final session of our Introduction to Malware series. Some housekeeping notes before we get started. A recording of this session will be available after the event, and a link to view will be emailed directly to all registrants. If you need assistance or have a question for Dr. Kurta during the presentation, please send us your questions via the chat window. We will answer as many questions as possible at the end of the discussion. Now, let's get started. Over to you, Engin.
Thanks a lot, Ashley. Hello, everybody. Welcome to the webinar today. So today, my plan is to talk about botnets, the number one problem on the internet. So originally, I was planning to do 3 sessions, but then I decided to present a bit more detail. And in future sessions, after these introductory webinars on malware, the plan is to start looking into more advanced malware and also solutions. What kind of research is going on out there, what kind of dynamic techniques are actually useful in practice. But that's something that we're going to discuss in future webinars. So botnets, as I said, are the number one problem on the internet. And whenever we see malware today, it often has botnet-like functionality that it's delivered with. A bot, sometimes they're also known as zombies or drones, is actually a compromised machine that can be controlled by an attacker remotely. So the key feature is that machine, that compromised computer, is remotely accessible to the attackers, and it can be remotely controlled by the attackers. So bots have 3 distinguishing features. They have a remote control facility. This is very important. They implement different commands. So whatever the bot master, the malware author wants it to do. And they often also have a spreading mechanism for propagation purposes. So these are the 3 distinguishing features. In the past, as when we looked at worms and other types of malware, bot functionality wasn't something that we always saw. A worm basically propagated itself automatically, but it was not remotely controllable. So today, a bot, a malware can be like a worm, so it can have worm-like functionality, but at the same time, it might be remotely controllable, so it also becomes a botnet. So a botnet, in essence, is a network that consists of several malicious bots that are actually controlled by a commander, and this bad person is often called a bot master or a bot herder. So the classic architecture would be you would have a collection of these compromised machines. Each one is remotely controllable, so it becomes a bot, and the attacker then is able to connect to these bots and is able to issue commands, and these bots then implement whatever the commands then are. So whenever a new machine is compromised, say a home user who's sitting at home, their machine after compromise becomes a bot and joins this botnet. So if you look at the historical evolution of botnets, the first bots, I don't know if you remember the 90s, they were actually invented for benign use. And often you saw these bots in IRC channels, right? The internet relay chat. So people were chatting there, and a bot was basically a script that sat in the background and was able to receive commands on behalf of the user, right? So when I left the IRC channel, I could leave my script running. That was my bot. And when people sent commands to it, it could converse, actually implement these commands. But a bot was also useful for letting that channel be open, right? So whenever you leave, the IRC channel closes, so the bot actually made sure the channel was always open. So that's where that was the first bot. But later on, of course, people realized, hey, you can have compromised machines with that can actually implement remote commands. So let's call them bots as well. So after a while, when compromised machines were acquired, people started abusing the usage of IRC for managing these compromised machines, and so that's why we started seeing an emergence of bots that were then connecting to IRC channels. So in the late 1990s, we started discovering remotely executable code that had botnet-like functionality. So we started seeing code that was bad, but that was also allowing remote access to attackers. People started calling them robots, but then later shortened them to basically bots. Also, in the beginning of 2000, we started seeing denial of service attacks coming from many compromised hosts, and these were actually first instances of bots that were actually being used in attacks. So today, botnets are the most serious and dangerous type of malware we see out there, and it's actually a big problem. And the chance that you see bots in residential networks, in universities, in companies is actually quite high, right? Whenever you see malware, it often has a botnet-like functionality. So here's a very simple timeline of botnets. Like in the 90s, you had these non-malicious IRC bots that were basically used to keep IRC channels open. But then we started seeing malicious variants of bots, bot code that was then basically used to manage compromised machines. And you might have heard of very well-known bots such as SD-bot, AgaBot, SpyBot, etc. Because this remote functionality, remote management functionality code was leaked to the internet. People could simply download them and then base their bots on them. That's why we started seeing a lot of variants of these, bots like AgaBot or FatBot. In the mid 2000s, we started seeing a shift to peer-to-peer bots, and different instances of bots that actually used a peer-to-peer infrastructure for sending and receiving commands, and that actually made it a bit more challenging to take down these bots. Today we see a mix of things. IRC bots that actually use IRC channel for being managed are less popular today. We see more peer-to-peer activity, more web-based bots, but also bots that can use arbitrary protocols designed by the malware authors to be managed. So what is the botnet threat? Well, information dispersion is a big issue. So email spamming. So most of the spam you receive today actually comes from bots. So bots are often used to send out a lot of spam, and you can actually rent botnets to spam people, right? So if I have a botnet, you can rent it from me, and I can then use it to send spam on your behalf. Denial of service attacks, that's also a huge issue. So bots are actually a useful weapon for the attackers to launch distributed denial of service attacks. So a classic way to make money is to blackmail people. So if there's like a website that makes money using e-commerce, you could potentially blackmail them and say, if you don't give me, I don't know, $500, I'll bring down your website. So that's actually something that's also done quite often. But we've also seen denial of service attacks against companies. Remember the WikiLeaks story where a number of credit card companies got denial of service attacks, and that were actually taken, that were not reachable for a while. It happened because botnets were being used in these attacks. We've also seen attacks for political purposes. For example, after there was a crisis between Russia and Estonia, and a lot of services in Estonia got attacked by botnets, and the claim was that these attacks were coming from Russia at the time. So botnets are also useful because of information harvesting. So if you can gain access to identity data on these compromised machines, you can look for financial data, you can look for private data, which then is sometimes used for blackmail. So we've also seen instances of that. You can go through email address books, very useful for spreading the bot, and any other type of data that might be present on the host of the victim that you can use in some way to make money. So if you're compromised by a bot, the thing to remember is that they can access anything, and they're often interested in anything, right? We've seen research papers where people have looked at what kind of data is collected by attackers, and they often collect, login data, everything they can get their hands on, not because they look at it right away, but they would like to store it, and at some point it might become useful. So the botnet characteristics would be a remote control facility. It would allow the attacker to have full control over the infected machines. And often you have a wide range of supported commands. So that would allow the attacker to command bots for very specific purposes, right? So if you think about it, if you design your own botnet, of course, you would like to have commands to be able to send out spam, to search the internet. You would like to have commands for taking screenshots, maybe, searching for certain files in the system, or launching denial of service attacks against a certain IP range. Also, you would be interested in having a spreading mechanism for further propagation. For example, you might be interested in exploiting vulnerabilities. As we said before, while remote control mechanism and commands differentiate bots from worms, they have very similar mechanisms, right? So you can have a botnet, but that's a worm at the same time. So the larger a bot is, the more effective actually it would be, and but at the same time it comes at the cost that, you know, if you have a large botnet, if it's taken down, then you lose all these compromised machines at the same time, right? So it's often a trade-off. The propagation is done by finding vulnerable victims, and we talked about these things before when we looked at worms and viruses, right? So you could do random scanning, you could do permutation scanning, you could have a list, a hit list of things or targets that you're interested in, or you can combine, you know, all these different techniques. So everything you see in worms, you know, social engineering, the tricks that we talked about in the last couple of weeks, you would also see in, you know, in a typical bot. So, you know, these things are all combined. So the most distinguishing and powerful feature of botnets are their command and control mechanisms, and often we call this the CNC. So as long as you have an update command defined for the bots, the bot master is able to change the command set by updating the bots, right? It's just like having benign software. You know, it's just like Windows has an update mechanism. Botnets often also have an update mechanism because this actually gives a lot of flexibility to the bot master. So it actually makes sense for them. And this update mechanism allows the bot to evolve, so the code can be changed and the changes can be pushed to, you know, all the compromised machines. And these changes are also useful if I have some new functionality, right? And I would like to push it to my bots, I can actually also do that. So the command and control brings a great flexibility to the activities that can be performed by the bots, right? Having this command and control actually means that you can manage millions of machines, you know, hundreds of thousands of compromised machines with the ease of your, you know, your keyboard. At the same time, if you think about it, the command and control is also the weakest link of the system. So, you know, if you start thinking about solutions now, the weakest link would be the command and control. And if you're able to take down the command and control, you're actually able to mitigate the botnet problem, right? Because yes, then you would have all these compromised machines. Maybe you can't fix all these individual infections, but if you take down the command and control, you actually, you know, basically take the botnet away from the bot master. So you can have different types of command and control, of course, and all these things are, you know, classic distributed systems programming, right? You could have a push style command and control where the bot connects to a command and control server, listens for commands, and then you can give commands to the bot. Or another popular technique is the pull style command and control. For example, the bot regularly contacts a website, and on that website you give the commands that the botnet should do, and it just regularly pulls commands from that website and then starts, you know, following those commands. We've also seen decentralized command and control mechanisms such as peer-to-peer. You know, in the evolution of malware, that was the logical next step, basically. So we had push, we had pull, but then we also started seeing peer-to-peer command and control, where the idea is that you don't have a central command and control server like a website or, say, you know, IRC server, but these the bots are in this peer-to-peer network. What's the advantage of that? The advantage, of course, is that it's much harder to take down, right? Because you don't have a central server. Basically, you can just unhook, so as the defender. So that's why we've seen the emergence of peer-to-peer botnets as well. And Storm is a very, you know, famous example of that. So the centralized command and control is actually quite straightforward. You have the bot master, and the bot master has an infrastructure of command and control servers that he or she maintains, and basically the bots connect to these command and control servers, and you basically just, you know, listen to commands given by the bot master. So where is the command and control infrastructure hosted? You know, you have different options. Basically, you can just go and buy, you know, virtual servers, and you can install your command and control infrastructure there. And one of the considerations you have there is, of course, you don't want the good guys to take down your bot infrastructure quickly. So you might go to countries that are actually more tolerant to this type of illegal behavior, right? So the command and control might be hosted in a country where, either the government tolerates this whole thing, or it might happen, or the government is just too slow to react to take down notices of the command and control infrastructure. Of course, you can have servers in different countries, so if one server is taken down, you can move your services to the other server, for example. In the push-style command and control using IRC, which was the classic popular thing that we used to see 5, 6, 7 years ago, the bot in this simple architecture, the bot connects to an IRC channel, a dedicated IRC channel that you have set up, right, on a server port and a server address, and then you can start chatting with your bots that actually listen to commands in this channel, right? So you could do something like ADV scan, LSASS, etc., or you can give like a denial of service attack to a certain IP range, a certain port, or a port range, and the bots listen to these commands, and then they might look for running processes with a certain with certain arguments, or you can tell them to denial of service a certain IP range, right? So the bots actually listen to all these commands. So IRC used to be popular, but the downside of IRC, of course, was that yes, the bots can connect to these IRC channels, but the good guys can also connect to them and start listening to what's going on in the botnet, right? And people have actually done this in the past to measure the size of certain botnets. So this tends to be less popular today. So you're seeing less and less IRC channels because they're also easier to take down. In the pull-style command and control, and this is something we're seeing quite a bit, the command is regularly pulled from a website. So the machine is compromised, and that machine might connect to a certain IP address or a certain domain regularly, say once every hour or once every half hour over HTTP, and then pull down commands that have been issued by the bot master, right? So again, this is effective, and one reason why this is effective is that the entire communication is often done over web, right, HTTP, and the challenge here in terms of research then is how do you distinguish between benign traffic and malicious botnet-like traffic? Because people are often allowed to connect to the outside using HTTP in companies, right? It then makes it a bit more challenging to find out, if the traffic that's going out there is actually coming from a bot or from a person. So that makes it a bit more challenging, and that's one reason why pull-style communication is actually popular, right? For example, if the bot would connect to the outside using a very unpopular port, say 10,200. That's something that would just pop up on firewalls, and it might even be blocked, right? And that's one reason why pull-style communication makes it easier to manage their infrastructure for attackers. So here's an example of a pull-style command and control using HTTP. So a page like this might be hosted at on a server on a certain IP address, and when the bots connect to this, you as the bot master can actually issue commands, and you can say things like, execute the shell command on all the bots, or start denial of servicing these IP ranges, and the bots connect to this URL, this website, and get their commands from this website. If you think about this style of communication, the disadvantage of pull style versus push is that push has the advantage that if I issue a command, that command is sent to all my bots instantaneously, right, at about the same time. But if I'm doing this using pull, then you would in theory need to synchronize clocks, because if I tell my bots to scan, they might not start scanning all at the same time, right? If they're connecting every hour, for example, unless they connect at exactly the same time, not everybody sees the command at exactly the same time. So that's one potential disadvantage of this type of command and control channel. So using peer-to-peer as command and control, as I was saying, was the next step. And it's the best example for decentralized command and control, where the nodes of the botnet behave both as a server and a client. And the advantage here, from the point of view of the attacker, is that if I can identify a botnet, I can take it down. The rest of the botnet survives, right? Because each can act as a server and as a client. For pull and push, if I can take down the website, or I can take down the IRC server, or the other type of push server, then the entire botnet basically is gone, right? Because I can, it's not able to receive commands anymore. But peer-to-peer makes it more challenging because each node can act as a command and control server. So peer-to-peer bots are more difficult to catch, and trace back. They're more robust, and even if some of the nodes in the network are shut down, the gaps in the network are closed, and the network continues its activities, right? Just by taking down 5, it doesn't mean that the entire botnet can be taken down. It comes at a cost, though, thankfully. So because it's peer-to-peer, the good guys have a chance to take over the botnet as well. So yes, peer-to-peer gives you the advantage that the botnet becomes more flexible, and it's more difficult to take down. At the same time, it's more difficult to control also for the attackers, right? Because of the way the whole thing is structured, somebody might be able to take over the botnet. So most of the well-known peer-to-peer botnets use an existing protocol, for example, Kademlia. So they go out and then they look at what peer-to-peer networks are popular, and then they start using that existing infrastructure. So the bots do not directly send information to each other, but publish a piece of information that is issued by the bot master whenever the bot master wants to perform an activity. And for example, a key would be the bot would look for a certain key every day at a certain time, right? For example, you would search for 32 different keys, or you would search for a certain key based on an algorithm, and only the bot master knows this algorithm. So if the bot master would like these bots to do something, the bot master would publish information with that key, and the bots would find that information, say it might be a text file, and extract the commands from the text file. So since the attacker knows which keys are searched for, he or she can publish the commands with the keys to be searched, right? So the idea is actually pretty straightforward. What's the downside? Well, the downside is that, yes, at some point, the defenders also capture a bot, and just by analyzing the bot, reverse engineering it, they can find out how these keys are used, how these keys are constructed, and just as the bot master is able to put commands into the peer-to-peer network, the good guys can also start putting in commands into the network. And we've seen research papers in the past where actually researchers have done that. So they've taken over well-known, peer-to-peer botnets such as Storm for a couple of days, for a couple of hours, and that has actually allowed them to gain insights into, how these botnets are managed and how these things are how the attackers actually control their bots. So interesting bot commands, at least 2 types are available. One is for denial of service attacks, for example, SYN or ACK flooding attacks. And another one is very important, the update mechanism, right? So if you have a bot consisting of hundreds of thousands of compromised machines, you want to be able to update these bots so that if you want new functionality, you're able to push it to them. So other popular commands are opening a proxy to send spam, or having keylogger or other identity theft functionality. So I can say, for example, search for a certain, search for credit cards numbers on all my compromised machines. So that could be a command. And then the bot would search for this information and then would just upload it back to me, to the bot master. So other bot features are, as we were discussing with malware, they use, of course, it's malware, so they use obfuscation, they use encryption. Most of them are packed, meaning, they've actually been obfuscated and encrypted. And, it might be UPX packed. There are packers you can buy out there that actually allow you to create malware that's very difficult to reverse engineer. For example, Themida is a well-known one where they use a sort of virtualization technique to run the malware, right? And as we were discussing in the previous webinars, it actually makes it much more difficult to understand what this piece of malware does, this botnet does, without actually running it and analyzing it dynamically. They also often have anti-debugging mechanisms, such as detection of VMware, the famous red pill, or detection of debuggers. Right? Often you attach yourself to the malware to try to understand what it does, and they might use anti-debugging tricks. And some of these tricks I would like to discuss in future webinars. So I don't know if you remember the matrix, but you could take the blue pill or the red pill. Red pill is, in terms of computer science, it's a very simple check to find out if you're running in a VM. It used to be very popular in the past. Today we have more virtualization support in hardware, so it's not as reliable as it used to be in the past. But in certain cases, just by running this piece of code, it can tell you if the code is being executed in a VM or not. And if you're running in a VM, the idea that Botmasters sometimes use is that if you're being run in a virtualized environment, there's a good chance that you're actually being analyzed, or there's some sort of a security product that is running you. That's why you change your behavior, or you just stop doing something, right? So that's another classic trick. So we're seeing actually different variants of this. At some point, I'm also going to talk about stalling loops, for example, that we've been seeing more, where attackers are using specific pieces of code that allow the malware to react differently in a sandbox, right? And as you know, many solutions today depend on sandboxes, depend on dynamic analysis, and that actually allows malware authors to bypass these defense techniques. All right, so this was the intro on botnets, right? But so how do we stop bots? So that's a classic question that you ask yourself. And there are a lot of industry researchers asking this question, but also scientific people who do more scientific work at universities who've actually looked at bots and who have come up with solutions to try to solve the botnet problem. So the current research, if you actually split it up, people have looked a lot at tracking botnets, right? So the first step was to try to understand what botnets do, how botnets react, what kind of information do they collect. So there wasn't much empirical information out there. So people have actually, hijacked bots. They've entered IRC channels. They've set up their own IRC channels. They've run bots to try to understand, how big these botnets are, how they're managed, so that we're able to come up with better detection techniques. So developing detection schemes has been a theme that scientists have actually looked at quite a bit, including myself. So, famous, well-known tools are Bot Hunter, Bot Sniffer, Notos from Georgia Tech that actually looks at DNS information. Exposure is a system that I worked on with some colleagues, where we also use domain names and how domain names are resolved to try to detect botnets, and also creating behavioral models that you can then use for intrusion detection, basically. People have also looked at developing super botnets, right? So why would you do that? Why would you, as a researcher, try to come up with very powerful bot architectures? Well, these are attack papers, and they're actually useful because that allow people to think in advance, right? Think before the attackers do, come up with more sophisticated attacks that could be possible, and then also come up with solutions that you can use to address this new problem. So that's something that is quite popular in academia as well as in industrial research. So tracking botnets, as I was saying, is useful because a crucial first step is to collect the malware, right? And people have set up honeypots in the past to detect, deflect, or counteract attempts at unauthorized use of resources. So you can have low interaction honeypots such as Nepenthes. In the past, used to be more popular. Today, these are not as effective because you're seeing a lot of client-side attacks rather than server-side attacks. But you can also have high interaction honeypots that actually are a bit more intelligent, that interact with exploits to try to capture malware samples. We also have spam traps. Basically, we look at content being sent over spam to try to identify malware or attacks in spam, like spear phishing attempts. And the malware caught by users and also by companies often, etc., are submitted to malware analysis platforms, and two examples are Anubis and Lastline. So basically, Anubis is the free open version of what we provided Lastline. And these are dynamic analysis environments that allow you to analyze the malware and to extract the behavior of the malware that you can later then use for detection, for example. So what kind of information would be needed to track botnets? Well, you can look at domain names and IP addresses of the command and control server, right? So you see all these interesting statistics that people provide, and then they might write reports, and then they might say, hey, a lot of command and control servers are hosted in, I don't know, country X today, right? So what does that tell you? Well, it tells you more or less what's going on the internet. It doesn't really give you deep insights, but it's statistical information that you can collect. If you have the nickname of the bot, the channel name, the decryption key, it might actually allow you to act as if you are a bot and then see the commands that the bot is receiving, right? And why is this useful? It's useful to understand, what the bots are doing. It's useful to understand because based on the commands that you're receiving, you might actually use this information to come up with better detection schemes, right? For example, an example of a detection scheme would be, think of the fact that you have a push infrastructure, right? So you have all these bots listening to commands. The bot master sends a command, and all these bots react to this command more or less at the same time, right? So you could actually use this behavior to detect botnets, right? Because the command that's coming in is usually very small, but then you see a lot of activities from different machines at the same time, right? Using a behavior like this could allow you to come up with better detection techniques rather than just using signature-based detection. So people have acted as if they're victims. They've contacted, they've actually joined the command and control server and to try to gain insights into what's going on in the botnet and how large this bot actually is. If you are in an IRC channel, you will actually see all the bots that are connected. So you would get a sense for the number of bots in that botnet. So what do you gain with the information you acquire by tracking the botnets? Often people can report the size of the botnet, the propagation vector, right? How does the botnet grow, and how does it actually propagate? You can look at what kind of information is stolen from the infected machines. Why is that interesting? Well, it's interesting because that gives you an idea of what kind of a bot you're dealing with, right? Maybe they're interested in credit card information, or they might be targeting online banking sites, right, or online banking users. So that gives you an idea that what the financial incentives are, or you could see that the bot has been mainly used for sending out spam. So you could look at the kind of activity the botnet performs or has performed to try to gain an understanding for what the bot does, and also to understand who's actually behind these attacks. You can try to basically guess that. But most importantly, as we were saying, mitigation or detection techniques can be developed based on a deeper understanding of tracking botnets. That's why we've seen quite a number of research papers where people have actually tracked botnets. And now we're seeing more papers and more research ideas on detecting botnets more effectively. So people have actually, as I was mentioning, tracked the Storm botnet, and also have tried to mitigate the bot by injecting polluting keys. So if the bad guys are giving commands, you as the good guy can also start giving commands that are harmless, and you can start disrupting the operation. For example, ideas have been proposed, such as routing infected users to benign web pages instead of the one that is controlled by the attacker, maybe informing them that they've been infected, right? So we've seen attempts like this in the past. You can have host-based or network-based detection, of course. The host-based detection, as discussed before, relies on antivirus software, relies on binary signature databases often. But as we discussed before, again, this comes with the problem that polymorphism is an issue, right? The malware evolves, it changes, and signature-based detection often is not very effective. And because of the update mechanism, actually, we've seen bots that change their shape, every hour. And because that happens, the code, the way the code looks changes every hour, and so the signatures become not very useful, right? So that's a problem from a signature detection point of view. So network-based techniques, or like intrusion detection, have the advantage that you're sitting in the network, so you don't have to do anything on the host. You might have network signatures, but lately we've also been using quite a bit of behavioral signatures that allows us to actually deal with changing malware, evolving malware, right? If the code changes, that's not a huge problem for us because we're actually looking at the behavior for detection. So domain names are actually also very useful for detecting botnet behavior. And our system that we created in the past, Exposure, that we ran online for a couple of years, and that quite a number of people actually liked, was using domain names and how certain features in domain names to try to identify command and control infrastructures for botnets. For example, this slide shows you how the domains being resolved by Conficker change regularly, right? So they have domain name generation algorithms. And in this case, Conficker was using randomly generated domains. But we've actually done research on this. We've extracted different features. And to be able to, we actually also are able to use domain names to detect suspicious botnet-like behavior. For example, because the domains that are being resolved regularly are look random, right? That's one feature you could use. Or we look at TTL values, and malicious domains tend to have lower TTL values because the attackers would like to have more flexibility. That's another thing that you can use for detection as well. So Exposure is an example of a system where we used this domain name features for botnet detection. Also, domain names are also sometimes used to, when the malware infects a machine, the DNS settings might be changed of the compromised machine, and users might be redirected to the attackers, right? So using domain names and features in domains might allow you to see this type of behavior and then use it in your detection of the botnet. So malicious services are often as dependent on DNS as benign services. So being able to identify malicious domains would significantly help mitigate many internet threats, right? When we were creating our system Exposure, this was one of our theses. So we thought, if you're able to effectively identify malicious domains, that would actually be great to be able to block the command and control rather than fixing individual infections. And another hypothesis we had was, when you look at large volumes of data, DNS requests for benign and malicious domains should actually exhibit enough differences in behavior that can then be automatically distinguished, right? So we use machine learning when we were looking at large volumes of domain names, billions of requests per day, or the requests of a certain organization or an ISP. We were then able to analyze a lot of data. So this is big data analysis where you're then able to use machine learning effectively. And if you're able to identify these features smartly, then it's not 100%, of course. Nothing is. There's no silver bullet, but you're able to automatically filter out domains in this huge traffic that are often being used by for malicious purposes. For example, by botnets. So what are these distinguishable features for malicious and benign domains, right? So that's a good research question that then comes up. If you look at large volumes of DNS data, what features should you look for? And a good example of that are actually fast flux detectors. So every time a domain is resolved, a trick that bad guys often use is that it resolves to a different IP address every time you look it up, because it gives them more flexibility, right? So it might resolve to a compromised machine sitting in an ISP. And this actually is this type of behavior. So every time you look it up, the IP address changes, is a feature that might indicate suspicious behavior, right? This by itself isn't fully reliable, because you might also have something like this for high availability purposes. But at the same time, this is one feature that might indicate suspicious behavior. And when you then start combining it with other things, for example, you see fast flux like behavior, but at the same time, you're also seeing domain names that look random. So when you start combining them and doing machine learning on these features, the results are actually quite promising, and the detection rates are also pretty good. So that's another question we were asking at the time was, can you create a live malware detection system by monitoring the DNS traffic of the network, right? Can you only look at the DNS traffic and then reliably say, which domains are malicious lookups? And it turns out, in practice, yes, you can do this. It's, there is a false positive rate. It's not, it's not zero, but it's actually quite acceptable. And if you then start combining it with other things that you're seeing, not only DNS, but also the way, for example, the executable behaves, that actually gives you quite a good detection rate. And for example, Exposure is a system that we built in the past that is able to do this only by looking at the domain names. So just some examples of popular botnets and botnet sizes to give you an idea, and then we'll stop there. Zeus is a very well-known botnet today. There are a large number of variants of Zeus, and well-known because the financial incentives there are to attack online banking. So gain online banking credentials. There are keylogger components. They actually steal information that is then used for making illegal profits. And at one point, it was reported to be more than 3.6 million compromised computers. Kubeface was using social networking sites to spread. It was reported to be close to 3 million compromised computers. Tiltserv was reported to be more than 1.5 million compromised computers, and it was spreading through email spam. So the thing to keep in mind here is that all these statistics are interesting, so it gives you an idea about how large a botnet is, but nothing is foolproof, right? So I would take these measurements with a grain of salt. Some of these botnets are large, that's what we know, but a large botnet at the same time is more difficult to manage. It can be taken down, so that's why bot herders, bot masters might actually run smaller botnets side by side, so they might maybe have access to different command and control infrastructure, because if one of them is taken down, the others still survive, right? So through better detection techniques, what we often see is that the number of compromised computers in a botnet, the number actually is reduced because detection becomes better, right? If the detection isn't good, we see larger botnets with larger numbers of machines. Okay, so I'm going to stop there today. So that was our introduction to malware. Now that everybody's on the same page, the plan is to start looking into more research topics, more detection type of stuff, more advanced malware in future webinars. If you have any questions, I'll be happy to try to answer them. And thanks for joining. Ashley, back to you.
Perfect. Thank you so much, Engin. That was great. If there are any questions, please enter them now through the chat window. We will hold just a minute. Okay, we have a question here. You mentioned tracking domain name or IP as a detection scheme. Wouldn't domain spoofing disable this detection?
Domain spoofing. I'm not sure how. Yes, I mean, okay. So yes, that's one technique, right? But in all the techniques that I actually talked about for tracking, for detecting, it is an arms race, right? It's something that shouldn't be forgotten. So yes, it can be bypassed. So when I was talking about exposure, for example, using DNS, for example, you use say 15 different features, right? Each of these features by itself can be bypass in a way, right? So for example, if you look at how domain names are evolving, if you look at fast flux like behavior, you might create a botnet that doesn't do that, right? So that feature becomes useless. Or if you're looking for low TTL values, then the bad guys start using high TTL values, so that feature becomes useless, right? But if you're doing this, you're actually increasing the difficulty bar for the attackers. So in a case, it becomes more difficult for them to maintain their malicious infrastructures. So yes, I mean, every time I actually give an example, you're right. It's good to think about how to bypass it. And yes, it can be bypassed. It can make tracking or detection more difficult.
Okay, perfect. Thank you. I'm not seeing any more questions come in, so we will wrap up here. If you have any questions after the session's end, you can send them to webinars@lastline.com. You can also learn more by visiting www.lastline.com/labs. Thank you all for attending. We hope you enjoyed the series.
Thank you, everybody. Bye-bye.